Thank you very much for the introduction, and thank you very much for hosting me in this wonderful city. As she said, I've been in the business for almost 42 years, but it's the first time for me to come to Istanbul. And thank you for the next 20 minutes of attention to the Western Digital Ultrastar enterprise storage brand and how that is useful in Ceph environments. And I guess the green one is forward, yeah. Since I'm going to touch on some future initiatives, I have to have a safe harbor statement here. Should you decide to invest in our shares and make money, you're welcome. If we change our mind and you lose out, I take no responsibility. I heard earlier that Western Digital was not very popular here, especially for enterprise products. But you must understand, almost half the world's bits reside on Western Digital hardware, be it in embedded chips that you might find in your mobile phone, or be it the consumer brand, which we really should be known for. And what maybe you don't know yet is that we have a very broad enterprise portfolio for use inside data centers. So let's cover the HDD portfolio. This is basically the toolbox we produce drives from. It starts with the HelioSeal technology that we introduced in 2013, allows the drives to have better longevity, lower power, and higher data density. We can fit up to 10 media inside the 1-inch C height form factor. We have a selection of different recording technologies, be it conventional or perpendicular, be it SMR, shingled magnetic recording, where you write sequentially in overlapping tracks, or ultra SMR. We have 3 types of actuators, either single arm, with an elbow, or even with a third stage that gives you more precision and allows higher density. We have different recording technologies, perpendicular or energy-assisted perpendicular magnetic recording. We can have 1 or 2 channels active at a time, depending on the model. And the SoC, the system on chip, either leverages DRAM as an intermediate storage technology, or our iNAND chip that you saw earlier, which we have branded OptiNAND for that purpose. So from this toolbox, we have 3 families that are relevant in the data center. For the highest IOPS density, you would go with the air-filled drives with capacities up to 10 terabytes, all 3.5 inch, all 7,200 RPM with a SAS or SATA interface. For lowest absolute power, you would go with the 12 terabyte helium-filled drives, leveraging the HelioSeal technology. And if it comes to highest storage density, we have 3 active families ranging from 16 terabytes to 22 terabytes for conventional magnetic recording. And going forward, we'll introduce a 26 terabyte drive, which is based on host-managed SMR, which means you need a special file system to run this. But at pretty much the same cost, you get about 4 terabytes extra storage capacity out of this design. Here, the family side by side. On the left, you see the technologies leveraged with the designs. And the 9-platter 16 and 18 terabyte is the one with the lowest power. The second one in the middle has the OptiNAND technology, which added a little to the power, and they did a lot for capacity, actually. And on the right-hand side, that's where we added yet another platter. So this is the one with the 2 platters inside. One case gives you 22 terabytes, gives you very high data rate because it uses the same technology on the recording side. And it gives you the so-called armor cache, which I'm going to cover in the coming page. What you see in the diagram is how data usually travels from the host to the media. It goes into the RAM buffer first, then it's written to the media, and once it's processed, the command complete signal goes back to the host, and only then can the host issue the next package to the drive. This is considered the write cache disabled mode, but it's also the save mode, because this way the file system will always know if data has been written or not and can recover from it. If you want more performance, you have to put the cache in the write back mode, where the drive goes to the RAM, command complete goes out to the host, and the next data comes in, even though internally the drive is still processing. This way we can reorder commands, be more efficient in how we lay out the data, and much faster. But if you have a power disruption, whatever sits in RAM gets lost. And that's what we solved with the introduction of the IronNAND chip, because this chip is fast enough to gather the right cache from DRAM in its entirety, 128 megabytes, based on the power that the drive generates from the spinning stack as it's spinning down. So with that combination, you will have safe data transport, and you'll have much higher performance, up to 565 write IOPS from a drive that would normally physically only do 80. Right? The actual seek of the ARM cannot do more than 80, but through command reordering and OpenInfra, we get to 565 write IOPS. And here's a side-by-side comparison. You see the various transfer sizes and how the throughput grows with and without Armor cache. But actually, I like this picture better because this shows you the percentage gain in throughput through OpenInfra based on the queue depth and based on the block size. So you see across the board very high gains, which can be as high as 80% in write throughput. Switching horses, Ultrastar platforms. We have specialized servers, either for data transport between data centers, because even if you have a very fast internet, processing a couple of hundreds of terabytes can take you the better part of a year, whereas the mobile servers, you can throw in a taxi and in a couple of hours you're done. And if that's not enough, we've even shipped them via UPS. So it is, believe me, the fastest way of moving data between data centers. The focus for today, however, is with the external HDD storage, or the Ultrastar JBODs. And I'll also cover NVMe over Fabric, our Data24 device, and the devices within which are our own networking SoC and target cards. We have two JBODs. The Data 60, which, as the name suggests, holds 60 drives, is a very compact JBOD supporting SAS and SATA HDDs as well as SSDs. Or if that's not enough, there's a slightly longer chassis accommodating up to 102 HDDs, of which 24 can be SSDs. What's a novelty is our drives always carried a 5-year warranty, but the various OEMs that are integrating them usually only pass on 2 years of that because they have their own processing times. When you buy it under our brand, you have 5 years warranty on everything, the chassis, the drive, the SSD, whatever comes in the box. And the typical use is for enterprise-grade big storage data, which can be backup, archive, surveillance, or other. And that's the reason for me being here. Software-defined storage is a big theme for us. There's some key technologies in that JBOD that I want to highlight. One is called ISO Vibe, where the individual backplane connectors are mechanically isolated from each other, which means there is no crosstalk, mechanical crosstalk between the drives. So if one does a seek job and the other one is trying to write a video, that can work without interruption. For comparison, typical vibration cost degradation is in the order of 25%, and with ISO Vibe, you don't see that. You have stable performance across the entire usage range. The other key technology is Arctic Flow. So here you see the JBOD. The front row column, or in this position column of drives, receives outside air, which gradually gets warmer and is then transported to the side and out, whereas the drives in the back get fresh air through the channel in the middle, and then it gets gradually warmer until it's blown out by the fans. What I'm showing on top, on the right side, is a competitive product that does not have that technology. So the drives are running hotter in some areas, which can lead to throttling, early failures, and so on. And on the bottom, you see the thermal measurements of the drives in our JBOD, and you can tell from that that this technology is very useful in keeping the drives at full speed and very reliable. The other focus in the design is ease of service. I'm actually showing our server, but JBOD and server are the same in that aspect. For those that ever have been in a data center, you know there's a cold aisle, which is noisy, but temperature-wise quite comfortable. But the hot aisle is full of cables, it's hot, it's noisy, you really don't want to go there. So there's big value that in our servers, you can change even the CPU blowers from the front by pulling out the chassis blowers, the SSDs, the I/O modules, and the hard drives. All that can be serviced from front. And it can be serviced toolless. And in any service situation, the lid stays in the rack, so you never have to bother yourself with that. You unlatch the handles, pull the unit forward, and you have access to the devices. The status LED on the chassis will tell you which state the device is in and whether it wants service or not. And the same is true for the HDDs. There's a little fiber bringing LED light up to the clip that's holding the drive, and that will tell you whether it's in rebuild, in service, offline, or other. Switching to the back, you can change the blowers individually. You don't have to replace the entire PSU as with other designs. You can change the PSUs where one PSU is strong enough to run the JBOD forever, but we strongly recommend if one breaks, get it replaced to have redundancy back in the system. And all the cables that are not visible on this picture, I'm sorry for that, are connected to the chassis, which means when you service the I/O module, you never have to pull the cables and then wonder which way they were connected, because they simply stay in place. You go to the front, pull the I/O module, and you're done. And you can pull the unit forward without worrying about the cables, because we do ship a cable management arm, so the cables never get entangled in the rack. And here's what all this is worth. The orange line shows one of our helium drives in a conventional design JBOD, and you see the first year had 0.45% annual return rate, which is not the failure rate of the drive. It is the false alarms plus the drive failures, so don't confuse these. And accumulated to the second year, you'll see 0.98% based on our statistics, but if the same drive is in our JBOD, which is the blue line, you see that the return rates are dramatically reduced. The original projection was 0.35 per year, and in our JBOD, we made the best drive perform even better because we're below our own return rate and failure projections with these numbers. And when I say the best drive, I mean it. There's a company, you find the link here, that is regularly publishing their return rates, and where we had 4 million drive days, or 40,000 drives for 100 days in one quarter, we had 76 returns, which translates into 0.64% actual failure rate or return rate. And the second best competitor has twice that. The other guy has over 3 times that. And what this also gives away, they might not be using our JBOD yet, because otherwise that number would be 0.19%. Here's a better view on the JBOD. You see it's very versatile in terms of connectivity. So if you want to install a Ceph-based object storage device leveraging erasure coding, you need quite a lot of compute. And I'm not aware of another JBOD that has so many ports that you can actually connect 6 servers to 2 of them. And when you follow the Ceph design guidelines, which means 1 core per spindle and 1 for every extra task to manage metadata, to manage repair jobs with it, which is the strength of object storage. Because object storage repairs defects before you even know about them. And that is if you run erasure coding, and in this scenario, if you run the 18/6 erasure code, you can tolerate any 2 servers failing. You can tolerate up to 6 HBAs going wrong, and you see the entire list. Under all these situations, you still have access to your data, so it's super robust. And also quite dense if you consider this is 14U in total and giving you 1.67 petabytes usable object storage. Switching to the NVMe over Fabric device, Data 24, there are 2 versions. One that has 600 gigabit connections, and if you do the math for the 24 NVMEs, there's no bottleneck, so you have full bandwidth from the SSDs onto the network. But some people don't want an RDMA network with switches and everything that goes with that. They would much rather replace a direct attached SAS JBOF, which can be done with the 2 times 100 gigabit version, because that makes all the NVMEs visible on these 2 ports, and will give you twice the bandwidth of SAS JBOFs at lower cost. From about 90 terabytes, the networking overhead is fully compensated by the better cost of the NVMEs that we use instead of SAS SSDs. It's managed either by a command line interface or a graphical user interface, and the specification is an open specification. So composable API was initiated by us, but it's available for everyone to use. These are the cores we use inside. The one on the left is in use today. It uses RDMA as a transfer protocol, or in other words, it can bring data from the NVMe into the memory of the server with very little CPU interaction. But many people said, RDMA is great, but I can only do TCP, can you help me? And that's what we're doing with the card on the right. So TCP traffic tends to have 10 times as wide a latency distribution, but if it's the only thing available, we better enable the customer to use it, which is what we're doing with this card, which will become available by end of this year. We double bandwidth on the networking side, we double bandwidth by going to PCI Express Generation 4, and we introduce a few additional functions, including that this can also work as an initiator. This one is only a target. You need another NIC to speak to the box. The new card can do both. And with that, let's go back to Ceph. I call it Ceph on steroids because, as I said, object storage is all about robustness and size. But with Data 24, it can also be about speed. So in this small setup with a shared switch, we achieved almost 20 gigabytes per second in terms of gets, and almost 10 in terms of puts, or almost 1,500 4 megabyte IOPS, which is quite impressive and actually limited by the compute part. We can do faster data transfer from the Data 24, but Ceph object storage tends to be very compute intensive. The typical setup in the data center would have dedicated switches for the storage cluster, the server cluster, and the clients. But even though for cost reasons we did a shared switch here, we achieved quite impressive numbers. And with that, I'm done. I hope I made up some time. I know we are running late. If you have questions, we'll be outside. We have one JBOD for touch and feel, if you don't believe the words. So come and see us and have a good time. Thank you.